Ladies and gentlemen, could I have your attention, please? It's a great pleasure for me to introduce the plenary speaker, Professor Carsten Scherer. Professor Scherer received his PhD degree from the University of Würzburg in 1991. From December 2001 to February 2011, he had been a full professor with the Delft Center for System and Control at the Delft University of Technology. Since March 2010, he has been SRC Semtech Chair of Mathematical System Theory in the Department of Mathematics at the University of Stuttgart in Germany. His main research interests cover various topics in applying optimization techniques for developing new advanced controller design algorithms and their applications to mechatronics and aerospace systems. Professor Scherer has been chair of the Ifac Technical Committee on Robust Control, has served as associate editors for the IEEE transactions on automatic control, automatic and system and control letters, and so on. He is going to talk about this dissipation-based controller synthesis, success and challenges. Now let's welcome Professor Carsten Scherer to deliver a plenary lecture.
So thank you, Mr. Chairman, for this very kind introduction. And I also want to thank the organizers of the conference for inviting me to come here and give this presentation. Actually, it's the second time after 2003 ROCON conference that I give such a plenary lecture in Milano, and I really enjoy being in this wonderful city. So today's talk is about dissipation-based controller synthesis, and of course, as some of you might expect, it will be about LMIs, basically. But I want to start with an engineering problem of more general interest. This will be about static optimization only, because it illustrates some of the features that are involved in designing controllers in this setting. So in engineering, we are all throughout confronted with optimization problems, maximizing profit, minimizing costs under constraints. And we all know that these problems are pretty delicate. If the involved constraint functions are general nonlinear functions, we cannot really handle large-sized problems easily. And the story is really different if the constraint functions become convex. Because under these circumstances, we are able to design algorithms that might work efficiently, and we can really handle such problems possibly in a globally optimal way. That's the big distinction. I mean, as Rockefeller has posted, the great watershed in optimization is between nonlinear and convex, and not between nonlinear and linear as we used to think of in systems theory. I want to be a bit more specific today. I want to look into more particular convex optimization problems when the involved functions are all affine functions. So the cost is affine and the constraints are affine. And they also take matrices as values, symmetric matrices as values. And then we want to interpret this inequality here as being negative semi-definite. And you might wonder, why do we want to look at this particular convex optimization problem as a generalization of linear programming? And the answer is actually pretty simple, because first of all, it's easy to identify affine functions, so we can really look at the optimization problem. We can easily identify as such the structure, in contrast to convex problems. And of course, that's also the reason why these constraints are called linear matrix inequalities, or LMIs. And again, I guess a major issue over here is that we have now beautiful solvers available for solving relatively large-sized semi-definite programs, as they are called, or LMI problems, as they are called. And we also have good parsers, meaning that modeling languages, modeling tools that translate a given optimization problem into the framework such that you can hook up solvers as you wish. So that's really something that you can set up on your computer within 5 minutes, and you can solve problems up with 10,000 even up to 100,000 variables if you exploit structure. So let's look at a particular optimization problem. I don't know whether some of you have ever been in the Kröller-Müller Museum in Arnhem in the Netherlands. It's world famous for its Van Gogh collection. But if you walk around in the park over there, you see this nice needle tower statue. This needle tower by Kenneth Nelson that he built in 1968. And that's actually a tensegrity structure. It's a truss consisting of wires and bars, such that not two bars touch each other. And of course, you want to make sure that this construction is actually mechanically stable. And all throughout engineering, of course, these problems do emerge. And we've got trusses to design such that they have maximal stiffness, and you want to use as little material as possible in order to construct these trusses. Well, here's my own little truss. I build it in simulations. If you apply a force at the tip, of course, it shows a certain deformation. And I exaggerated a lot. Material constants are for steel, and of course, this is really multiplied by a factor of 1,000 or so, such that you see something moving. Okay. So how would we go along in order to model an optimization problem that's related to this? Well, we'd look at the cross-sections as decision variables. We would put up a mathematical model, and mechanical engineers would tell us, okay, and there is this stiffness matrix involved. And here is something interesting. The stiffness matrix is actually affine in the decision variables, in those cross-sections. And you apply an external force, you've got a deformation of your truss as a reaction, and this is just kind of Hooke's law, very straightforward. In order to maximize the stiffness of the truss, you could, for example, try to minimize the stored energy. So if you have got some force, you try to minimize the deviations, the displacements that result from that, and that could be done by minimizing F transpose D, for example. And we get an optimization problem as usual. But here is the interesting thing in this problem, as I think physics tells us that not all stiffness matrices are suitable. So we have to obey this constraint that the stiffness matrix has to be positive, semi-definite, and all of a sudden we are in the area of semi-definite programming. But this is a nonlinear problem, of course. And so this would be the formulation of the problem, but it's nonlinear in nature, so we couldn't really handle big-sized problems of this type, at least in principle. And you could go along and eliminate, for example, the variable D out of your problem. You get inverses of matrices, so the structure really does not simplify a lot through this simplification. But here's a little trick from linear algebra, namely the Schur complement formula. I couldn't miss out on mentioning that over here. That turns these constraints into one matrix inequality constraint, and all the variables now show up in an affine fashion. A of x was an affine function. The upper bound that we want to minimize over here is as well entering linearly. So it's not this particular problem that I find interesting over here, but it's the fact that we have to massage engineering problems as they emerge in order to turn them into semi-definite programs or LMI optimization problems. In this case, you can now handle decision problems, decision variable sizes of 10,000, 50,000, up to 100,000, they say, with standard tools. So I did run this optimization problem on this little truss, and of course that took only like milliseconds to do that, and you could improve the stiffness of the truss by a factor of 2. And that's an optimal design. What's interesting, what we observe is that it gives us a certain sparsity structure in that truss as well. And you might say, okay, that's only a toy examples, or that's not really of practical relevance. Well, there is a prominent example, namely the ribs of the leading edge of the Airbus A300. They are designed by convex optimization techniques. And they could reduce the weight substantially by using those tools. So it is really applied in engineering situations. Let's now turn to dynamical systems. And let's move on to dissipativity. And the first thing I want to remind us of is how we would look at closed systems, systems that do not interact with their environment, and how we would try to guarantee stability, check stability of such systems. And if you allow me to use this animated cartoon, we of course would choose a Lyapunov function, kind of an energy function, and we would try to make sure that the energy always decreases in our system. And that proves stability. Standard fact, we all use it on a daily basis. Now, Jan Willems has been generalizing this concept to open dynamical systems, systems that interact with their environment through inputs and outputs. And then, of course, if we look at the same pictorial representation, it can happen that during the movement we add energy to the system. So you add energy to the system, you extract energy from the system, but overall, dissipativity means that the initial energy in the system plus the supplied or extracted energy should be larger or equal to the final energy in the system. That's the dissipation inequality. That characterizes dissipative systems. Of course, we have to formalize this notion. So that means we have to introduce a system description in state space, let's say. We have to specify how we want to measure the flow of energy into the system or out of the system. We do that by a so-called supply rate. That's just a function of the input and output that characterizes the actual power, or is an abstraction of the power flowing into the system. And then dissipativity would mean, on a more formal basis, you need to find a Lyapunov-like function, a storage function, such that this dissipation inequality holds true, which means energy at the initial time at state x of t1 plus the integral over the supply rate, that's the supplied energy to the system, should be larger or equal to the final energy after the movement, v at x of t2. And this has been a generalization, an abstraction of the classical concept of passivity. In RLC networks, we naturally have inputs to systems like via ports. And we could view, for example, the voltage across a port as an input to such a network, an electrical network. And we could use as an output the currents into the ports. That could be options for choices. Of course, there are generalization and variance, Wave variable transformations, and so forth. But that's the simplest picture that we might think of. And then the supplied power to such a network just means, well, it's the power in electrical engineering, just current times voltage. So that would be the supply rate we be using in this context. And then dissipativity just means the classical notion of passivity. So you can subsume this passivity notion to the general concept of dissipativity. And for linear systems motivated by this example, and that's basically what I want to be talking about during this presentation. I want to concentrate on linear systems, but I want to also introduce nonlinear elements in the picture. So for linear systems and quadratic supply rates, you can easily show that you can prove dissipativity when your system is dissipative via a quadratic Lyapunov function. And so it doesn't really cause any limitations to use quadratic Lyapunov functions. Well, this is the dissipation inequality that we have to verify. This is, of course, based on checking all the trajectories that can occur in your system. You have to verify this dissipation inequality. And as usual, we would go to an algebraic version thereof, so the differential version. And that would result into a pointwise condition on your inequality. So that's just a condition on all x vectors and u vectors that emerge over there. And as it turns out, and as we can easily read off from here, all functions are quadratic that are involved. So this really does turn easily into the corresponding representing functions of these quadratic functions, representing matrices of these quadratic functions, to be positive semi-definite for x, for example. So this pointwise algebraic version of the dissipation inequality turns into an LMI. And what's interesting here, this storage function does really enter linearly. So this is really a nice LMI that we can check. So we can go to our computer and have it verified for us. And passivity, for example, emerges as a particular version thereof. And this leads to the classical positive real lemma. So this is basically the dissipation inequality that will pop up all around in the SQL, that will show up all around in the SQL. It's the algebraic version of the dissipation inequality. I want to see variations thereof and what we can do with it. So it's actually quite amazing, I think, how wide the range of applications of this conceptual framework is. And of course, many people here in the room have done much deeper work in translating, like for a given class of storage functions, the dissipation inequality into computational tools, into algorithms that are amenable to computations. So I just gave you the most simplest, most basic picture thereof. But the recent example is some of Scherer's programming, the last item on the list. There you would look at polynomial systems, these systems that is described by polynomial functions. You choose polynomial supply rates and polynomial storage functions, and then the dissipation inequality would translate into polynomial inequalities. And we now routinely know how to turn these into linear matrix inequalities. So that would be a nice example of such a generalization. But of course, we want to make it work for us. So we want to do something with it. It's nice to have this conceptual framework, but we want to really solve problems, if you like. And I want to go back to a very classical subject, namely the subject of absolute stability. And well, it's on the cover. It's the features the latest Control Systems magazine, so it's still of interest to people. And of course, in such a setting, we look at such a feedback interconnection of a linear system in the forward path, a nonlinearity in the feedback path, and we want to guarantee stability under hypotheses. And typical hypotheses are sector bounds on the nonlinearity. So how would we go along from a dissipation framework? Well, we would choose the right supply rate related to the sector bound. And here it's kind of obvious. Just use u square minus y square. Why would we do that? Well, because on the graph of the nonlinearity, this supply rate is just non-positive. And why does that help? Well, if you take trajectories, if you integrate your supply rate, the energy integral will be also non-positive. And if you can then prove dissipativity of your system on the other side, and you interconnect the two components, both relations are valid, you can sum them up, and you just get the usual decay of the storage function. Hence, you have proved stability in this way. And it's as simple as such. So you cover the information about the nonlinearities in your supply rate, and you prove in this fashion by a dissipativity argument that your system is stable. So that would be kind of a sufficient test for stability of your interconnection. And it turns into an LMI. We know that. We don't need to write it down anymore. It also is related to a frequency domain inequality, because we have a KYP lemma, the Kalman-Jakubowicz-Popov lemma. It, of course, translates into the Nyquist curve of the linear system being contained in a disk. But we wouldn't do that from a computational point of view. We would rather say we stay with the LMI, solve that, because that tests stability. And the nice feature of this is, now, first of all, it, of course, gives us robust stability against all nonlinearities in the sector. And in contrast to classical frameworks, it easily generalizes to robust performance. So whenever you have an extra channel in your system and you want to impose an extra condition on performance, like that the energy of the output is not larger than the energy of the input, an L2 gain constraint on the performance, then you can actually just write down the corresponding dissipation inequality, and it's as simple as just adding the corresponding supply rates. The first part is related to performance, the second part to the uncertainty. You just add them up, and you get robust stability and robust performance guarantees for your system. And here's actually a proof based on dissipation. So you start at rest, as we usually do for performance, and the dissipation inequality then just implies, if we integrate from 0 to infinity, that, well, this overall integral over all the energies involved is non-negative in this case. We know something about the uncertainties because the uncertainties about the integral over the uncertainties is non-positive. Hence, we can drop the last term, and we have proved our gain bound. So that's really relatively straightforward to do. And the nice feature of this framework is that it generalizes to complex interconnections. And we have seen lots about complex systems. I had the power grid as an example for a complex system. That involves, of course, the interconnection of many, many components that we cannot model in all their details. So we try to only capture the essential features of those components and still prove overall stability of such a massively interconnected system. Another area of application is systems biology, molecular systems biology, where you build compartment models and you also try to capture only the essential features of each compartment, and only out of the interconnection you try to make sure that the overall interconnection of your system has desired features like stability or even like cyclical behavior, like in circadian rhythms as they emerge. So these techniques are applied in this direction as well. How would you go along for such complex interconnections? Well, an abstraction would be we distinguish the known components from the unknown components, and in robust control we like them to denote by deltas. The unknown ones are where we have only partial information about. And we split these two up, so the G contains the known parts, the deltas, the uncertain parts, rough information is available only. So if you would proceed and would try to do something computationally, you would simply choose certain supply rates for these deltas. So for the delta K, its supply rate, as we have illustrated it for the nonlinearity. And of course, then you could just say sum them up. But here's another issue that comes up. Just summing them up, applying kind of standard small gain or passivity arguments, is conservative, leads to bad tests. So we should improve on these tests. And there's a classical way of doing so. Instead of just summing them up, you take non-positive linear combinations. And that's obvious because, you know, the integrals over the supply rates are non-positive. And you take positive linear combinations, you get non-positivity of this combination. So it's a very simple argument, and you've got stability also there. And the key thing is through this TOS, this is actually a version of the S procedure as it's known. Through these TOS, you get a much better test typically than by just applying standard small gain arguments. And it turns into computations. So you can also search over your storage function and your multipliers right away in one shot. And that's what we call the multipliers in robust analysis as they show up. So let me give you an example how we would apply those techniques for practical purposes and here on a classical interconnection. Let's suppose you've got your classical control configuration, you've got a saturation at the input of the system, a delay at the output of the system. How would we do that? How would we analyze such a system? Well, if these blocks are very small, so they're as tiny that you can hardly see them now, then you would just go ahead and verify, choose your tests, and I show you one possibility to choose this test, to choose supply rates in order to capture the properties. But we now know also that we can refine those tests. We can really construct much more complicated tests. For example, by introducing dynamics in those supply rates, by using filters. So there's lots of families of supply rates out there for particular nonlinearities that we could include in this framework. So I chose Same-fault multipliers for the saturation and dynamic descalings for the delay. And just two examples, and I want to illustrate what happens if you just look at small perturbations. You have these small saturations, you scale it down, you scale the delay down, and you just run your algorithm like a Nyquist test, but with a computational tool of convex optimization in between. And you can, of course, prove stability of your interconnection. That's straightforward for small perturbations. But then you inflate those, and as it happens, the weak test, the bad test, fails at some point. Of course, this is not strong enough. All tests are sufficient in general. This is not strong enough to prove stability, and we also see nothing happening in the system. The step response does not show anything of this instability. But our good test, our better test, the more powerful test does still show stability. So we can move on. And in this example, it happens that we really hit the stability boundary. And so this would be a test, a computational test for a robustness margin against these structured uncertainties where we hit the stability margin. So this is an example where you are non-conservative in your test. And people often say these tests are overly conservative, they're really too crude, but it happens, and it's an interesting research question, still ongoing research question, to verify when these tests are exact. That has been, in a historical context, also studied by many people, but there are still very beautiful mathematical questions involved to understand this phenomenon for more general classes. So let me just summarize what we have seen. And this framework of capturing the uncertain components or the rough information about the individual blocks and the performance specification by a supply rate, choose classes of storage functions and turn that into an LMI. That really gives us kind of a timeline of history in robustness analysis, starting from small gain in the 60s, passivity, circle criteria, that's been done in the 60s, moving on to multipliers towards the end of 60s, 70s, and structured singular value emerged in the beginning of the 80s until integral quadratic constraints in the 90s. A beautiful framework, and I think the key thing is, for nowadays application, its modularity is really useful for handling also more complex situations. And it extends to synthesis. And that's something basically from the 90s and the last 2 decades, roughly speaking. I don't want to look at controller synthesis. I want to rather look at observer design. Just because the structures are so nice as they show up, as they emerge, and we don't need to do many manipulations, as you will see. Of course, we know that observers are all throughout, and they are typically used to clean signals from noise. And the Kalman filter is, of course, the classical example that we all learn about. They are used in fault detection. I remember the crash of the Ariane, or the explosion of the Ariane 5, and that was actually caused by the fact that the measurement system of the Ariane 4 was taken over into the Ariane 5, but the flight path was different. That caused a too high aerodynamic pressure, and then this resulted in a conversion mistake, a conversion error, and that caused the explosion of the aircraft or the rocket. So in fault detection, these things are relevant, of course. We see emerging issues like in distributed sensing and observer designs, and where these techniques are also applied. And it's, of course, also interesting to use model-based observers whenever we have highly uncertain components, like in biological systems, as I have been arguing. So how would that go along? And that's now just classical ideas, of course. We've got our system with a disturbance, with a to-be-estimated variable, a measured output, design our observer in order to reduce the effect of the disturbance on the error. And we write down for a system description. I chose a linear one for simplicity here. We write down simply a copy of the system, and we try to design our observer again for the aerodynamics. Very standard. Now, the goal would be to enforce a certain performance specification from the disturbance U to the error Y. And this performance specification, now we have flexibilities because we can express that in terms of an arbitrary supply rate that we might want to choose, for example, an L2 gain supply rate, and we write down the dissipation inequality, and that's it. So this would lead us to the dissipation inequality for designing the observer. And here is the troublemaker. We do not right away end up with something that's nicely linear. But here, it's really obvious how we would do the transformation to linearize That's straightforward. It's just a variable substitution. That's bijective. We can go back and forth. And we turn this nonlinear inequality into something linear, into an LMI in the variable x and n. What's the message over here? Well, this technique does generalize to output feedback synthesis. It does generalize to stochastic criteria. It does generalize to many other issues that you might apply those techniques. So this is an illustration of the transformation technique that convexifies an originally non-convex problem. We also want to design robust estimators. Well, if your system is corrupted by uncertainties, is affected by uncertainties, you cannot just take a copy of your system and design an observer. That wouldn't work because you could not implement it. That's why you have to design estimators, filters that are not structured as an observer. And we are very lucky that the synthesis inequalities are just identical. So we can just take a copy of those from the observer. So for an estimator, you can start thinking about robust estimators. How would you proceed? Now it's basically the same steps. So you just choose the right supply rate. I added here performance plus those for the uncertainties. Conceptually, it nicely goes through. And you can design robust estimators as routinely as before. And again, the key thing is here that we have much more general ways of handling this in the same context, of covering nonlinearities and uncertainties in this context. Well, you might say, okay, estimators do have a particular structure. Is that really so useful to be able to design robust estimators, or at least is it not too limiting? Actually, what turns out, how we would look at the problem nowadays, is we would simply take a specific interconnection that we are working with, and I just indicated 3 of them, and we will put these into the generalized plant framework. And generalized disturbances and this interconnection structure, how the system is involved in the interconnection, we will put that into this framework. And then this red block, this controller, could be an estimator, could be the object to be designed. And if you put your particular frame design problem into this generalized plant framework, actually we recently found a nice answer to identify which problems can be handled by convex optimization techniques, which robust problems can be handled by those techniques. And it's actually very simple to say, namely these green blocks are the ones which can be affected by uncertainties. And only the blue block, as it appears over there, should not be affected by uncertainties. That's a limitation, admittedly, for sure, but many, many particular problems are covered by this structural situation. For example, robust estimation, robust feed-forward designs, uncertain weights. So if you've got coloring filters and they're affected by uncertainties, you want to design robust estimators against coloring filters. That's covered by this generic structure over there. Anti-wind-up design is another example. People have been looking a lot into systematic anti-wind-up design. That would be covered as well by this situation. Okay, often it is, of course, not possible to design robust controllers that are not affected by or are independent of the uncertainties, because they are overly conservative. So you don't get the performance that you would like to have. That's why you want to move on and to design gain-scheduled controllers. And actually, I want to illustrate what gain scheduling does for us and how it works on this intermediate experimental vehicle, IXV. Actually, ESA and Thales, they signed a contract in June 2011 that they want to really build this vehicle. And we have been involved in a project on verification and controller design for such re-entry vehicles in a European consortium. And what happens for these vehicles, that you see large dynamic changes when they enter the atmosphere in the dynamics of the vehicle. So you see large changes in the dynamics. And the classical approach would, of course, be to just cover the flight path by small environments, design local controllers in each of those neighborhoods, and switch. According to my knowledge, for example, during takeoff of the Ariane 5, they really switch hundreds and hundreds of controllers. So that's what's really happening in practice. Instead, and people at ESA are interested in these questions, you would like to cover the trajectory by larger neighborhoods, by larger areas, and adjust your controller continuously along the flight path. And that's what we would call gain scheduling controller synthesis. And in this framework, this is also called linear parameter varying controller designs, because we look typically at linear systems where this parameter enters the data in a possibly nonlinear fashion. So, okay, for our observer synthesis problem, well, here would be the setup. Our system is depending on this external parameter, this delta, as I call it. It's time varying. We know bounds on it, so we have a priori given bounds on this delta available. It's time varying and online measurable. So up to t, I have information about this delta. And the idea is then to feed this delta through to the observer and design parameter-dependent observers, such that they can really adjust themselves to the corresponding variations in the system. And the problem is the same as before. Try to reject the disturbances from the error, for example, by reducing the L2 gain, or use any other of the performance criteria that you wish to use. So in the dissipation inequality framework, we will just write down the corresponding dissipation inequality. Well, the difference now being that our parameter here enters the story. So we should robustly satisfy this dissipation inequality. Well, here the parameter varies in a box, so I assume that this inequality should hold true for all parameters in that box that we started out with. Of course, you need to make hypotheses on the system, on the dependence on the parameters. So here I take affine dependence of the A matrix. I want to design the observer gain, also affine dependent on the parameters. And now the coefficients are to be sought. So I want to search the coefficients in the observer gain, such that they're adjusting themselves on the parameter. Okay, so you just plug it into your dissipation inequality, and we get the same trouble as we had before, namely these nonlinear terms. But as you see, luckily everything goes smoothly away. So we can transform things away, and we get to convex constraints. Well, here's a problem. Here's an additional problem, because we have an infinite family of inequalities to solve. That turns into linear matrix inequalities, but that's an infinite family, because you have to choose or to check to make sure that this inequality holds true for all deltas in your parameter set. And because the delta enters linearly, we are lucky in this case, because we can just replace the whole box just by its corners, by its extreme points, and we reduce the whole story to just 4 linear matrix inequalities to be solved, and we're done. Again, this is the simplest version of generalizations that have been done in the last couple of years. We now understand how to handle polynomial dependencies on the delta parameters. We understand how to even treat general nonlinear dependencies by using specific relaxations. For example, sum of squares relaxations could enter the picture here as well. So this is the simplest version of a much more general story that's sitting behind. Let me give you an example just to illustrate kind of the point of view of how we would like to apply those techniques. A very simplistic example with one unmeasurable parameter, one measurable parameter. So these are the two uncertainties. And if you design a nominal estimator and you neglect that there are uncertainties in your system, you get a large error. So these uncertainties really hit you. Instead, you could design a robust observer. So that means you can reduce the error, but as we see, the effect of those uncertainties is so big that we cannot really reduce the error to a good degree, to a reasonable degree. That's why we should rather take measurability of that parameter into account to improve the performance. And if we measure this parameter online, design a gain scheduled observer, you get better errors, as we see in the blue curve. So it's really a reduced error, But still, because it was a nominal design, so we neglected the unmeasurable uncertainty in this design, we still get an error that's too large. What we can now do is we can simply combine these two and we can design robust estimators. And I wouldn't be giving the example if the result wouldn't be satisfactory, that we keep the error really between the bounds that we wish to have. So again, it's not the example, it's the philosophy that I want to mention here or stress here. We can really do these things. We can design nominal estimators, robust gain scheduling estimators in one common framework with the same computational tools. Actually, this gain scheduling problem is convex when all your blocks that are affecting your system are affected by uncertainties, and in this case, parametric uncertainties. But in recent years, we have seen lots of activities in, as I discussed, for controller synthesis in trying to merge robust and gain scheduling synthesis on one side. Also, there has been quite some activity on scheduling on more general blocks. If you think of anti-wind-up designs where you know the nonlinearities and you want to have your controller depend on those nonlinearities, such you get improved performance. Multiple objectives have been considered, and of course you see more and more applications emerging in this area of gain scheduling control. The key thing is, I guess, this design framework, or with this design framework, you really try to extend this modularity that we have seen that's true for analysis towards synthesis as well. And that's kind of the goal in this research direction. Well, I'm painting a pretty positive picture of the whole story, as you might have seen. And there are, of course, challenges involved. Challenges that came up over the years. We have quite some experience in practically applying those, and I'll be mentioning one example in a second. And according to my experience, actually, the biggest challenge is numerical reliability of the techniques that we have available. We have all these solvers around. We can really use them quite easily, but actually, it's extremely hard to make them work, it's difficult to make them work for advanced applications. And the key thing is numerical accuracy. And so whenever you solve such optimization problems, you never solve them exactly. You always have like little perturbations, little errors on your right-hand side. And I indicated that by this epsilon over here. Problems in control are very sensitive towards those perturbations. That's the observation. So the cost depends in a very sensitive fashion on this epsilon, and epsilon positive, epsilon negative decides about stability or instability. So it's crucial that we hit the boundary. And the solvers that do exist are just unable to achieve this reliably for the applications that you want to look at. The next challenge is in terms of structure and their translation into algorithms. So I've talked about complex interconnections that you want to handle. They show structure, they show interconnection structure. So if you build a system description, you get structure in your system description. But we understand too little how this would translate into algorithmic structure for implementations and to render these algorithms more efficiently. So we had a much less hard time to apply those techniques when we had this framework. What I would say what we needed is really LMIs for control available. And so we really need specific dedicated solvers for linear matrix inequalities in order to handle these troublesome situations in control. Here's an example that we have been working on, and I just want to illustrate that these techniques do really have their merit in practice. So this has been a micro-manufacturing technology project where we try to build high-speed spindles for micro-manufacturing. This is actually a commercial spindle over here. And this is the spindle that we built at my former place at Delft University of Technology. And our goal was rather to showcase the applicability of these LPV design techniques. And so this was an actively magnetically A and B spindle, so it was levitated by active magnetic bearings. It had flexibilities in it, and our goal was to suppress the disturbances that were incurred by the rotations of the spindle. So if the spindle rotates, this causes, of course, disturbances. You want to suppress those, but we wanted to speed up and slow down the spindle. So I just show results for speeding up the spindle. And hence, speeding up the spindle means we use this rotational speed as a scheduling variable for our controller synthesis. So we schedule our controller on this rotational speed and their variations. And for that purpose, we used LPV designs. So it was a full multi-input, multi-output synthesis approach that we took. And we chose weights to do this dedicated suppression of the disturbances by adapting the corresponding notch in the weight according to the rotational speed. So you see here, a figure of the weights. So you see frequency over rotational speed, and that's the family that they chose. And here you also see that the one body plot of the system that, experimental measured body plot of the system that we've been looking at, that we've been working with, and you see the resonances showing up there as well. So what we did is we designed controllers, and we implemented those and had the spindle speed up from standstill to 12,000 RPM in 60 seconds, which is quite substantial speed variations. And what turns out is that we compared LTI controllers with switched H-infinity controllers, so well-tuned LTI controllers with LPV controllers. And you see that these are real experimental results. If you look at an LTI controller, you've got an error that's larger than by designing this dedicated, for one rotational frequency, dedicated H-infinity controllers that give you optimal suppressions of the disturbances. But what you see is through these switchings, you get this zigzagging behavior of the error. And the LPV designs allow you, these gain theorem designs allow you to create this very smooth behavior over here. And so we had to give up on performance a little bit. That was due to right half plane zeros. They caused limits of performance, but we could ride through the resonances without any trouble. And we had to play a couple of tricks over here. For example, these are unstable controllers that we implemented for the best possible performance. Okay, so this is an example that demonstrates that you can really implement those LPV controllers in practice, and they give you the benefit that you expect because they hit the frozen design, they hit the actual H-infinity designs, the best possible ones. If we were able to perform this control synthesis, to apply these control synthesis algorithms to bigger systems, there are many, many potentials. I talked to people at ASML. That's the biggest manufacturer for wafer scanners worldwide. And they do routinely apply mu synthesis, identification mu synthesis experiments. Do that within 5 minutes in the loop. They would love to be able to apply these LPV techniques in order to take position dependence in their mechanical structures into account. But because of the difficulties inherent to the algorithms, that's really a trouble for them. But I know that's actually close to industrial implementation, that people use the LPV designs for controlling nonlinear systems like a robot here, and that might even go into production very soon. And these design techniques do have implications for distributed controller synthesis, where you want to design a distributed controller structure for a distributed, like a ring structure, as we see in the figure over there, which have applications, for example, if you want to design massively distributed controllers like in adaptive optics applications. And recently, we were also able to look at time-varying interconnection topologies and do something with these techniques about that. Okay, I'm already about to conclude. I was set to stay in time, actually, so tried my best. And I want to actually conclude with 2 remarks. I think this dissipation-based controller analysis and synthesis framework really has turned into a methodological technology nowadays. And I hope I could convince some of you that it might be interesting also for your own work to look at that framework. And as a last remark, I mean, I'm often told by people, well, you know, these LMIs, I don't like them. They're really huge and I don't see any structure. But believe me, and I hope I could show you a little bit of that, there is really structure inside. Thank you very much.
Professor Scherer has just given us a very interesting lecture on dissipation-based controller synthesis for uncertain systems. If you have any questions concerning the lecture, he will be happy to answer after the session. Okay. To conclude this session, let's thank Professor Scherer again. I would like to thank you all for attending this lecture.